Welcome back. This is in continuation to the previous video lecture where we have discussed the Coulomb's law, where Coulomb's law states that the force between two charges is equal to 1 by 4 pi epsilon naught epsilon r into q1 q2 by d square. Now you can see the question. What I have asked to find the force of interaction between two charges spaced 10 cm apart in a vacuum. If it is a vacuum, then automatically epsilon r is equal to 1. The charges are given as 4 into 10 to the power of 8, 4 into 10 to the power of minus 8, 6 into 10 to the power of minus 5. If the same charges are separated by the same distance in kerosene, what is the corresponding force of attraction? Now how to solve this particular problem? Now if you carefully see, the charges are given as q1 and q2. These are q1 and this is q2. And this is the distance between them, given as 10 centimeters. And this is epsilon naught. Now, so we know q1 now, q2 now, d we know, and epsilon naught, we know the value. Epsilon r, for vacuum it is 1 and for kerosene it is 2. So I'll directly substitute these values, and what I'll be getting? I'll be getting this 2.157 newtons. Whereas in case of kerosene, since epsilon r is 2, I'll be getting as 1.0785 Newton. So this is the simplest way of doing the things when point charges are given for us. Since there is only one particular charge, I haven't considered the unit vector, but you are supposed to consider the unit vector also. Now in the next problem, we will see what is the significance of unit vectors. Now this particular thing, you can see that there are three equal positive charges of 4 nanocoulombs, which are located at three corners of a square, side 20 centimeters. Determine the magnitude and direction of the force experienced by a positive charge of 1 nanocoulomb, which is located at remaining corner of the square. Now let us suppose this is a square. This dotted line represents a square, and these are the points A, B, C, D. Now I am considering A as 0, 0, 0, B as 0, 20, 0. This is 20, 20, 0. This is 20, 0, 0. Now let us suppose A, B, C are the locations where you do have the charges of 4 nanocoulombs. And this is the location where a charge of 1 nanocoulomb is placed and it is experiencing forces from these charges. So the direction of the forces will be, this is due to A and this is due to B and this is due to C. So all these forces will be in line with they will be aligned to the line which is joining these charges. So now we will compute first of all each of these forces. We will compute FAD, we will compute FBD, and then we will compute FCD, and then we will join all these forces. And here there are three different forces, right? So you are supposed to compute the vector component also, so that you can add them freely. Now let's compute the first one. So this is the description. The location of the three charges are Q1, Q2, Q3. So this is Q1, this is Q2 and Q3, and these are the locations which I have mentioned here. Now, see, these are the locations A, B, and C, D. Now, let's see the calculation of force AD, which is the force exerted by the charge at A on the force which is located at D. See, this is Q1, 4 nanocoulombs. This is Q1 nanocoulomb. So this is here. It was 4 nanocoulomb Q1 charge. This is Q1 nanocoulomb, and the distance between them is 20 centimeters, or about I can take it as 0.2 meters. Okay. So distance between them is, see, it is 20 minus 0, x coordinates 0 minus 0, 0 minus 0. So square root of x square plus y square plus z square. So 20 centimeters, or I can write it as 0.2 meters. Now the force, you know the formula, you substitute everything. So what you will be getting? You are getting somewhere around See how to compute the unit vector. See, this is a component unit vector. So how to compute the unit vector? The simplest way of computing unit vector is x1 minus x2 into I bar plus y1 minus y2 into j bar plus z1 minus z2 into k bar by square root of the magnitudes. Again, whatever the magnitudes which you get, this is the simplest way of computing the unit vector in xyz formats. This is UR. So this is what I have written: x1, x2, y1, y2, z1, z2 or these coordinates 0, 0, 0 and 20, 0, 0, and I have applied here, and this is the answer which I have got. It is 0.8 micronewtons. Now similarly for FAB, I am considering for FBD. So force due to charge at B on B. So it will be in this direction. So see the distance now, it is just like a diagonal of a square. So that's why the distance is 20 root 2 or 0.2 root 2. This is the answer. And I have computed this one. See how much I am getting. It is 0.318 microfarad into C. It is I minus J. Similarly for FCD. So where it will be? No. It is also again somewhere around 0.9 microfarad. But at the direction, see here, minus J. Now what you are supposed to do? You are supposed to add all these things. As I already said, Coulomb's law satisfies superposition theorem. So the summation of all these forces. So the first case of what I have got, 0.8 micronewtons into I bar. This is 0.318 I minus A, and this is 0.9 minus A. So summation of all these things, what I will be getting? This is my force. 1.2168 micronewtons, and the direction is I bar minus J bar. This is my force. Okay. So I hope now you are able to compute the force of attraction between two point charges using Coulomb's law. I want you to compute to solve these problems. You practice them at home and come back to tomorrow's class. If you do have any doubts, we will discuss in the class. So this is the second problem. Try to solve this problem also. Thank you. In the next video lecture, we will discuss about the computation of electric field intensity.